And I'm gonna admit some random, oh no, we got Nirav, not random. Right. Right. So I think everybody here knows of Tushar. He's been with our lab now for 8 years. Is it the 9th year? Oh my gosh, I'm losing track. You came here first in the summer of
2018.
18. Okay, all right. So then, yeah. So there you go. And when he was still, a master's student with the EU Maya program, and then he came back the next spring to actually do the master's. The summer was like kind of the middle of the master's thing, and then he did his actual master's thesis with us the following spring of 17.
18.
Sorry, 19.
19, yes.
Okay. I can't count that far back. Yeah. And then he got his master's degree, of course, and stayed on and worked as an associate in research for about a year, a little bit over a year, actually. And at that point, joined the PhD program this would have been
21.
21. Okay. All right. So now he's finally coming to the end of this many year saga, I guess. I won't try to do the math, but where you've been a master's student, a summer intern, a master's student, an employee, and now a PhD student. Tushar comes from Bangladesh. He has always been this very humble, very cheerful, positive influence in the lab. And at the same time, he's been doing very rigorous I will say, almost groundbreaking research. And it's been a real pleasure having him here. So normally at this point, we kick everybody out and talk about Tushar privately. If it's okay with the committee, let's maybe wait until afterwards. Neil, you're online, right? So I guess then without further ado, I'll turn it over to you. And then the rest of you, yeah, if you want food, just kind of do it quickly and quietly, and then we'll get this show going. Go for it.
Thank you. Thank you, Dr. Lowe. Yeah. If everybody get the food, maybe I can then start.
Get started slowly if you don't mind. I mean, it's a little distracting, but then I don't want to keep waiting. We do have a second defense happening right after this. So
yeah, sure.
Hopefully.
The people online, can you hear me well? And can you see my screen shared?
Yeah.
Thank you.
Oh, believe it just really correct.
Hello, everyone. Good afternoon, and thanks for being here and having time. My name is Fakrul Islam Tushar, and my work focuses on improving lung cancer detection and diagnosis. And I can begin by explaining why this matters, why lung cancer matters. Lung cancer is one of the leading causes of cancer-related death worldwide. About 1 in every 16 Americans will be diagnosed with lung cancer in their lifetime. And every couple of minutes, someone is receiving this diagnosis. So it motivates the need for earlier and accurate detection and diagnosis. Luckily, the computed tomography, radiography images such as chest X-ray and computed tomography has proven to be effective in early cancer detection and reduce mortality. However, to scale this up to everyone, we need tools that effectively detect and diagnose and support radiologists and improve consistency. So over the past few years, we have seen AI has changed everything that we do every day. AI is powering the tools that we use every day, but whatever the radiology, how well this adaptations has really resulted in the field of lung cancer screening and detection. There are AI tools that for lung cancer screening, but we can see that there's a very little use of this tool in routine practice. But what is the reason for that? There are many reasons, but what we found from our research perspective, there might be 2 main reasons. One, data and the reference standards are limited. Why I say that? Most of the data this model trained out there came from single source or derived from certain single source. there are very inconsistency in the reference standard, ground truth or the labels that we are using. And in many cases, many of these data sets have very poor representation of the abnormality that we want to diagnose or detect. So this is one of the bottleneck. The other problem is that evidence and the trust are very limited. We have very few trial-like multi-center evaluation for this model. Outputs most of the time feel like a black box. You get the output, but you cannot explain it, why it's happening or how it's happening. And it's very hard to find the failure when it's finally deployed. So this gap between the technical progress and limited clinical adaptations is the core problem that my dissertation is trying to address. So over the next hour, I will try to move you through this outline and trying to connect the different stories and outline how we are trying to solve this problem from weak supervision to virtual imaging, AI benchmarking, and synthetic generative AI perspective. Let us begin with the weak supervision. This is actually where most of the clinical data set or study begins. We do have a lot of existing data in our EHR systems, suppose raw CT images or radiology report, but what about the annotations? So you can see, here's a picture. Getting annotation is a hard job for humans, especially for the radiologists. It takes very much time to get it. For example, here you can see a CT scan and the associated radiology report. Now, what you can do, you may have already noticed, there is a lung nodule in the left lower lobe. Now, what you can do, you can get a bounding box around these lesions, or if you want more stronger, you can get a pixel level segmentations. So these are the form of strong supervision. Versus the next you can do, you can go with the radiology report and you can get this and you can say, there is a nodule in the lung. So here, this is a form of weak supervision where you have minimal to no locations and the label applied to the entire organ or the patient. So this is the main idea of the weak supervision. And now the question is that how far we can push this weak supervision. This is the questions. To answer this is produced as multiple first author journal and conference publications. And I was fortunate enough to win one of the Pratt poster award. So I will next few slides, I will walk you through what are the works that we did in this study. So our purpose is to design a multi-disease, multi-organ classifier that can extract labels from radiology report. And we can train a multi-disease classifier for body CT. How we did it? We get a lot of radiology report. Using this radiology report, we designed a rule-based algorithm. It is not a very difficult thing to do, but what was clever here that we had to build a dictionary that has different organ names, different diseases. Fitting that dictionary to rule-based algorithm, it can go by each of the sentence of this radiology report and can give you the organ labels. For example, here I'm showing you an example for the lungs. We are doing 4 diseases: atelectasis, effusion, nodule, and emphysema. And absence of any other disease, this 4 and any other disease, we call it a normal. So we get this organ labels. After we get this label, we can locate so sometimes we have the chest CT, sometimes we have chest, abdominal, pelvis. When you do the lung classification, we don't want to get a CT from the liver. So we used a segmentation model to get the volume of that target organ. Once we have that volume, we trained a very simple ResNet-like architecture. I want to remind that this study we're doing back in 2022. That time we didn't have very huge cards or anything to train a very large model. So we designed a very simple architecture to do multi-disease classification. And what this model does, it does, giving a CT scan, it can classify, give you the probability of each of these diseases. What do you think it is? So after we done all this, what is the key results that we got? We made some manual validation under the guidance of Dr. Rubin, and Vince was one of our very long-time collaborator. He helped us to get a manual validations of 900 CT cases. And using those manual validation, we find out that our rule-based algorithm is 90% accurate. And applying this rule-based algorithm, what we got, we extracted 19,000 organ labels from 12,000 patients. Here in this figure, you can see we got 19,000 organ labels came from 13,000 CT scans and 12,000 patients. And here you can see we get it across 3 organ systems: lung, liver, and kidneys. So after we get it, we use these labels to train a multi-disease classifier. And here you can see the result of that classifier. The performance ranges from 0.6 to 0.9 for different organs. For example, for the lungs, you can see the best performing class is effusion, and the worst performing class is nodule. And we sort of expect that because it's very hard to learn a nodule from a very big volumetric patch that you are giving. Here is an example, just showing the performance of the model. The bold word is basically the ground truth class or the reference standard that we are giving. It's a positive for nodule and emphysema, and you can see that is getting the output. Now, we did some follow-up studies after that to understand what is the limit of this weak supervision, how far we can push this weak supervision. What do we find out that? This kind of weak supervision labels, the model you trained with, they can sustain up to 10% of the added level noise, because we know that as you are extracting these labels from rule-based algorithm, there will be some noise or error in the label. And how much data you need? We find out that around 75% of the training data, the model performance got plateau on the test set. So you don't get any improvement in the performances. What is interesting that what we found out that using these weak labels, if you train binary classifier, they always outperform the multi-label classifier. But this kind of interpretation can be misleading. The reason is that binary classifier actually confounded by the co-occurrence of the diseases rather than the learning the specific disease. Why I'm saying that? Here I can show you an example. Here, the very big rectangle in the blue, you can see is the nodule performance for the multi-label classifier. It's like around 0.65 AOC. Every time nodule is co-occurrence with emphysema, you can see the performance goes bump around 90 here at this bar. So now you can see the problem, right? So you can do weak supervision binary classifier, but you have to be very careful when you interpret this kind of results, because confounding co-occurrence diseases really influence the performance of this kind of models. So what I would say in the conclusion of, if I give you a very high level overview, what is the conclusion and what is the takeaway of this weak supervision? We can scale up our data with this kind of rule-based algorithm with a huge margin. But you have to be very careful when interpreting the result, because your classifier can be confounded by the labels. So,
can I ask a question?
Yeah, sure.
You're characterizing that as a negative thing as far as characterizing the algorithm. I get it. But isn't that the reality of the world? Isn't that the same thing also affects radiologists?
Yes.
The fact that they would probably detect the cancer better when there's emphysema? Isn't that the reality? So what's wrong with it?
I think that the problem is that if you say that, okay, emphysema is a confounding factor, I would say that is a better term. But if you translate as the model is getting AOC for nodule detection 90%, I think that is misleading. So that is we are trying to transfer, is that this. So the main takeaway is that this weak supervision works, but you have to be very careful when you interpret the result for a specific disease that you want to learn. So emphysema and nodule, they confound it, but you should be very careful when we claim that 90% performance for the nodule.
I mean, I would say for that specific disease, you are still doing fine. The only problem is that your claim is dependent on the training algorithm that you have used. If you use a data set that doesn't have emphysema in it, then you would have overstated your claim.
Yes, so yes, that is the point, that we should be aware of this kind of limitations. That is the thing that we have shown with this study. Yeah.
So we
Yes.
don't know whether it's actually detecting the nodule in this case. That's the problem. Did you ever add a little bit of supervision in there to try to, or did you ever evaluate whether it was actually finding the nodule in order to make the claim?
So it misses most of the time. If I go back to this figure, we did try to exclude all other diseases, only for the cases where they have just nodule, not even the other diseases. Here I'm just showing 5, but the dictionary that we have, it has like 50 plus lung diseases. So what we have seen that it does, but the performance is very bad. It's basically by chance in terms of nodule if we do this kind of weak supervision.
So it can't identify, for instance.
Yes, it cannot identify because the nodules are basically between 4 to 30 millimeters, and it's a very huge volume to find a nodule in terms of weak supervision that we find out.
Sure, but if you added a small amount of strong suits, then maybe it would.
Yes, so that is the follow-up study that we did actually. That's we realized that what is the limitation of this kind of study and how we can introduce more stronger supervision. That was the next studies that I'm going to present. Yeah. So now that we have talked about that, now the next question is that how we can establish evidence when our reference standard itself has unreliability in it. So this chapter is all about establishing that evidence, and we'll talk about the virtual imaging trial. So before we go into virtual imaging trial, it's very important to understand what is a screening trials or imaging trials. So to go that, imaging trials are one of the very fundamental steps to establish clinical references or evidences. If we talk about one of this trial called National Lung Cancer Screening Trial, it's one of the biggest trial that changed the landscape of lung cancer screening. What was that? It happened over 10 years in the US populations. It has nearly 50,000 populations, and they're trying to compare the effect of CT compared to chest X-ray in detecting lung cancer and how much it can reduce the mortality. And what they find out, using CT scan for lung cancer detection can reduce the mortality around 20%. So that was huge. That changed the complete landscape of the lung cancer screening. But there are some challenges to this trial. It ran over a long time and is expensive. There is radiation risk associated to that. And there are like follow-up requirement. You have false positive and underdiagnosis or overdiagnosis. So is there a way that we can minimize these challenges and maybe can still get sort of the evidence that we want? Virtual imaging trial could be an option that we can go with. So to understand a virtual imaging trial, we first need to, yes.
Tushar, so I'm sorry to interrupt.
Yeah, no.
You can finish your sentence. What is overdiagnosis?
Overdiagnosis, like the false positive rate is so high, so that the patient might not have cancer. It might be benign nodule, but he might go through multiple rounds of screening, considering that to be cancer.
Deductible.
Yes. So yeah, so it's sort of a part of that one. Yes. The overdiagnosed, that patient got overdiagnosed around that many percentage. False positive is like about the detected nodule, how many of them end up becoming cancer or no cancer?
So they're related.
Yeah, they're very related to each other. Yes. And this is statistics are from NLST. Yeah. So to explain any clinical trials, a screening trial especially, you basically have main three components. You have a populations that go to a screening center, they get some images, and there are expert readers like radiologists that detect or diagnose. Now, if you want to replicate that in a virtual environment, you need to replicate all these three components in a virtually. So you need a screening population to a virtual screening population. You need the real scanner to be replicated in a virtual scanner, and you need sort of a virtual reader. In our cases, most of the time, AI or image analysis models. So let me walk you through how we actually did it. And this is the work that we have done in last year or so. And we're very lucky that we are one of the first to replicate the National Virtual Lung Cancer Screening, which is sort of inspired by the National Lung Cancer Screening, how we can replicate the entire process in a virtual environment. I was privileged to do some presentation in the conferences, and we won a Best Poster Presentation Award at VITM. I might show you this poster at the very end of my presentation. So let's look at what we actually did. What was our purpose? So what do we want to do? We want to enhance the lung cancer screening by emulating the entire process of imaging and detection in a virtual environment. And how we actually did it? First thing, we need to get a virtual populations. To getting a virtual populations, every patient has a CT scan. From this CT scan, we have a tool developed by Lovesun. It has three components. It segments each and every body part of a human body. And then we do all the segmentation doesn't work all the ways. So we do some quality control here. And then finally, after that segmentation passed as quality control, we make a 3D representation of this segmentation. So that is sort of our virtual patient with some texturization and other things. Once we have this virtual patient, this is the patient with no disease and anything. So then we have a tool called X-lesion tool, where you can define the size of the nodule, location of the nodule, and what type of nodule is the new version. So now Cindy has added, we can make very different kind of nodules now. But earlier version, we just had two types, homogeneous and heterogeneous. So we added that too. So we defined that. So after doing all this process, what we had 290 plus virtual patients with 500 lesions within it. After we have this, all our virtual patients, they have gone through a verified simulator called DukeSim developed by Dr. Abadi. And as we are trying to emulate NLST happened 20 years back. So we try to replicate some of the properties of that era, and we call that Duke legacy scanners. So we try to replicate some of these features in the images. So finally, once we have these images, so we are done with our virtual cohort and virtual images. Next thing is the virtual reader. To develop our virtual reader, we use clinical data. We use two of the open source public data set called Node21 and CXR, and we developed two different models. One is 2D, one is 3D for each of the modality, chest X-ray and CT, using the same hyperparameters, almost everything same except the data. Is sort of the concept is that is the same human reader trained with two different kind of modality. And then once this model has trained, we used our simulated data with this model to get some detection. So now we have all this three-step done. So now look at the, what's the result? What do you got finally the output in? Here are some examples of our simulated images. In the first row, these are the phantoms. I'm showing you just the axial view. In the row 2, we have the simulated images, and here's the zoom version of the CT and a nodule. And here is the chest X-ray. And it's just hard to visualize nodules in chest X-ray. So yeah, it's just a little bit hard to get it. So the next thing, let's see what is the key results after we have all this. So after doing all this, I said we have 294 virtual subjects, 174 was with nodule and 139 without nodule. And the ages of the patients that we mapped to a virtual populations, they're around 49 mean, and like 55% was male. And the nodules that we have inserted in this patient, this distribution was inspired by NLST. We have gone through the data statistics, what the nodule they have found in NLST, and we try to replicate that distribution. And we have two types of nodule, homogeneous and heterogeneous. So after doing all that, we pass it through DukeSim and we got 1700 CT scan. Why this 1700 CT scan? We have two scanners, two Duke legacy scanner, and we did 3 different configurations of different properties of those images. So you multiply 6 with 294, you get that. For chest X-ray, we just have one variance. Because that time, the problem was that we didn't get the proper data from NLST to replicate, to see there what is the property of the real data. And now the fun part, you can see the performances. So you can see the CT detection performance was AUC 0.92. And we also analyzed what is the performance for each of the disease type. Homogeneous lesions shown better detectability compared to heterogeneous, which may make sense because it might be a little bit harder. Same we can see for the chest X-rays, and the performance is a little bit lower, what we expect. So now, is this trend the trend similar to the NLST, the trend we have seen? Let's see. So here you can see that our performance here, it might be smaller to see. So here you can see that our CT performance is better than chest X-ray. So it's supporting the trend, what we have seen in the NLST. And for other diseases also, it is the same. But the next thing that we did, so now we have shown that it can mirror the trend of the clinical trial, but can it trend the actual point that we have seen in the NLST? So in the NLST, we don't have an AUC curve, but what we had is that we had one sensitivity and specificity point for the CT. And luckily, our performance is going actually on that point. So we can sort of say that our virtual lung cancer screening trial has mirrored the evidence that NLST has shown in terms of performances for at least for the nodule detection. So far what we have shown that we can emulate the evidence that the clinical trials show, but can we also use this virtual platform for sort of objective evaluation of the data, AI model, or any kind of image analysis model? We did one of this study. So the motivation of this study is that during COVID-19, we have seen there is a huge number of papers coming out, 99% EOC, 98% EOC, and like we all got blown up, like what is happening? But when you put these models into the actually some other testing, they completely go mad. And like the performance is so bad that I don't want to even show here. So what is the reason? So we wanted to use this kind of virtual platform to evaluate some of these models. So we pull a huge amount of data ourselves. We trained model on different data distribution. But what we are trying to analyze that what was the effect that driving this kind of performance differences? What we have seen, the performance is very much subject to the size of the abnormality you are detecting. If your abnormality is larger in size, having larger portion of the volume of your lung, all the models sort of, no matter if the model is trained with the smaller data or large, they perform relatively better. But the moment the abnormality goes down smaller, they don't sustain the level of performance. Here you can see the larger lesion performance and smaller lesion performance. There are like 4 different kind of model trained on very different kind of data, where United 10 is a very large model same model trained with 10 of thousands of COVID data. The next thing that we did, which was very unethical to do with the real patients, is that we compared this modalities like CT and chest X-ray. We put the same virtual patients under CT and chest X-ray, but in a magnitude of dose, which you cannot do with the real patients. And what we have seen that the doses, here you can see the doses magnitude, right? It might be very less visible, but here you can see this chest X-ray has a very bad quality compared to this one. And this CT almost looked like a photon counting. Not photon counting, but much better than this one. So what is the interesting finding that we get? We expected that CT will be better than chest X-ray, but what we found that this models has no effect. Dose effect doesn't has any effect on the performance of these models. So that was here you can see the performance are more, this is the AOC performances and this is the 95% confidence interval. And you can see that all the performance are within the range for chest X-ray and CT. So dose doesn't has any clear effect on the performances. This paper is currently under review at JMI, SPIE, Journal of Medical Imaging. Hopefully it will be published soon. So the takeaway message for that, virtual imaging trial can emulate the evidence in the real clinical trial, can mirror certain aspect. So what is the utility and impact? We can use it for personalized trial and can do the objective evaluation for the models, data, or for image analysis tool. And the future direction could be we can enhance the virtual cohort and maybe the diversity in the lesions. I have in the very end of my slide where in the emerging studies, we are looking at some of this. I will go next.
So just a
yeah.
question for you. So
Yeah.
COVID studies show that the
Yes.
magnitude of those have very little impact on the detection of COVID.
Yes.
Either for radiography or for CT.
Yes.
Is that what you have expected?
I would have not expected. So that is a very different evidence that nobody have showed it so far, because people had during COVID, we had the data like everywhere. People are sharing data, but we know very little about the imaging properties of this data. So far, we have not expected that. We might have shown that with the high dose, you have more cleaner images. It might be better to find the lesion easier, but it turned out to be for the pixel level, the model don't really care about those at least for the COVID. I'm not telling it for all the diseases, for at least for the COVID, which is our objective evaluation, it didn't matter.
So, I mean, that sort of challenges your premise in that in the NLST or VLST trial that you did, you congratulate yourself that I got replicated the real human trial in 6 scenarios.
Yes.
But then you're saying here, your algorithm does not behave the same way that humans do. So how do you put them together? they seem like they are, essentially, if this trend doesn't match what we see in real human trial, how can you trust any of these algorithms to be replicated in real trials in the case of NLST?
I think that is a very, very, very real challenge that we all are encountering, and we might be all are working towards that, because I think we have the doctors, they are already in such a level of performance, it's very hard to match that performance. And the other way that we really cannot see how this kind of black box are looking into the facts that we want them to look at. There are certain aspects that we can constrain them, that we try to do in few of our next studies, that how we can like constrain what is the effect of the data, what is the effect of the model, and what is the effect of the reference standard in that. But it is very hard to like explain why that is happening. But VIT is sort of a step that where data is our evidence. We can characterize the model based on the data that we are feeding it. And with the VIT, as we are simulating it, there is a very outer effect or other confounding factor. For suppose COVID, I'm sure that the COVID that we generated, that patient just had COVID. It doesn't have any other confounding other diseases which might influence the performance. So I can objectively evaluate those models based on that disease. I think that is a data-centric way that we can evaluate this model, but yes.
I found this result challenging.
Yep. Yep.
So, Tushar, maybe you have explained this. I'm curious, why do you limit to like 294 or whatever, a small number of population in your virtual screening trials? What constraints limit you to smaller population? Why
Yes.
can't they use a larger one?
Yes, so that is a very good question, and that's the questions we ask all the time. So the main problem was the computation, I would say. To get a virtual patients, there's a very multi-step process that we have to go with. We have to go with the segmentation of all the body and the quality control and the texturization. So on an average, to make a virtual patient on cluster, it took us like almost a day, I would say. So now you can do like, so that is now we did a parallelized computation. So that's why we could have reduced that time a lot. But at the time that I was doing that study, virtual population computation was the main bottleneck that we had to. That's why we did constrain that to 294 patients.
So you are saying the computational constraint.
Yes.
Does that mean if you have a lot of like GPUs, you can?
Yes. This is one thing that we are trying to get to the cluster of the national laboratories that we can make like thousands of patients. So that is, I was also trying to, so the like few of the very later studies that we have did, we at least try to get like this population to thousands so that we can compare. But if we get very high resources, we can generate this, we can make like as many populations we want. The computation was the bottleneck. That's why we are in 294 patients.
I see, but the whole process is automatic. You don't have much human involvement.
Yes. So when we did this project, that I had to like do it a lot of project management to connect different parts. But over the last 1 year, Milo has developed Gemstone. Now we can do most of this project automatically. So now it's automated. But when initially we're doing this project, all these three parts was separate. We had to do like connect different softwares to do this whole process. So that also what was a bottleneck that was contributing to the computations. But now luckily we have everything under same umbrella that called Gemstone. We can do end-to-end all of this.
Okay, thanks.
So I think I have already talked about the takeaways. So the next thing is that now that I have shown you that we can do trial-like evaluations, the next question is that what is the performance on the real clinical data for lung cancer? Because how much simulations we do, the reference, we always have to evaluate on the clinical performances. So that end of the day, people will ask. So if we look at the lung cancer AI and the studies, we will see there are like many studies that use one single data set is Luna-16, which we have also used. It's the most famous data set in the lung cancer study image classification detection. So this data set has roughly 900 plus CT volumes, have 11,000 nodule 3D bounding boxes for each of this nodule. But what is interesting about this data set, the diagnostic level for cancer and no cancer is a visual scoring. What is a visual score? Here you can see a scale of 1 to 5 between benign to cancer. So every time a candidate of nodule comes, there are multiple radiologists score it. If the average score is 3 or larger, it called a cancer. Otherwise, it's a benign. So this is the visual score that have. And why I'm going so deep into that explaining, later when I will show you the performance, you will see what is the effect of this visual scoring compared to other. Next, what I have already talked to you about, the National Lung Cancer Screening, is one of the largest data with 25,000 patients in the CT cohort. They went through 3 rounds of screening. So you have roughly 75,000 CTs, but they don't have any annotations. But there are a number of studies we contributed open source annotations for NLST. One of the study was by Michel et al. It was the Cybele study. They shared roughly 11,000 2D bounding boxes from NLST from 1,100 patients. So we did a little bit contribution in that. What we did, we took their 2D annotations and concatenated it into 3D bounding boxes. And we released that data and we thank them for sharing it. So after we did all these concatenations, we've come up with 900 plus patients and then 1,192 3D annotations. And for each of these nodules, what we have the patient labels. So there could be one patient, there could be multiple nodules. We don't know if this is the primary one that they have annotated. So there was some confusion in it, but patient level, we know that is cancer or no cancer. And then there's a very recent data, Luna-25. It is also a variance of NLST. It has 2,000 patients. It has center coordinate of the nodule, X, Y, and Z. It doesn't have the bounding box, but it gives you the center coordinate. And you have like patient, you have a follow-up or histopathology labels. Follow-up labels for the benign nodules and histopathology labels for the positive ones. Now you can see the landscape, the data set available there for different kind of study. So what is the challenges here? There are very few large, well-annotated data set. Data set is a huge problem in the space of lung cancer. And most of this data set has been derived from the same sources. And most of the time what people do, intentionally or unintentionally, train on the same variance of the data and report the performance. So you don't get a sense of what is the external performance of it. So we found a scope that, and the other problem that we found out, there is no open source replicable reference benchmark performances for detection or classification. What you can get and reproduce the result and can benchmark your results. So that was a huge problem. So we find a scope that how we can improve that. So with the help of Mike Harris and Dr. Tina and Aviva Wang, we created a data set that we have released. This is one of the most modern and largest lung cancer screening data out there. We made a reproducible public open access benchmark on the detection and classification, and we evaluated those benchmarks across multiple data sets. So I'll walk you through this. So out of this work, we were fortunate enough to release this data set at Radiology AI in data resources. And this benchmark paper is currently under review at Radiology AI. Our data set has been well accepted by the community. It has been downloaded 2,000 times from Zenodo, and we are talking with multiple companies. They want to get this data to make their model better. Our works have been downloaded almost 300 times, and people are asking questions over GitHub and GitLab, how to get these models and use this as a benchmark. So let's talk about the Duke lung cancer screening data set. This data set has 2,000 patients, over 3,000 bounding boxes around the nodules. And for each of this nodule, we do have actionable labels, is cancer or no cancer, and associated demographic. How we did it, the dissection model I developed in the very first study, VLST, we use this model and get the data from Duke, and I ran that model with this data. We got some pseudo labels with the help of math student under the guidance of Dr. Mike Harvitz and Tina. She annotated, she has gone through all the pseudo labels And what we did also, the rule-based algorithm I developed in my first study, that can also extract the sentences associated to each of the nodule. We also delivered that to her. She have gone through each of the annotations. It was painful. And she divided them into 4 different groups. Is the model is right, model is wrong, model has missed, model has annotated. So after doing all this, we get this data set. And you can get this data set in Zenodo and the benchmark here, the barcode. So now the next thing we want to do is that we have made this data set. We want to evaluate how useful and what is the impact of this data set. That's why we went to that benchmark. So we did 2 types of benchmark. We did a detection benchmark and classification benchmark. Let's go with the detection benchmark first. So the task of the detection, giving a CT scan, it will detect the nodule and give you bounding boxes. We trained with our DLCS data and we evaluated on Luna 16 benchmark our contributed NLST 3D data set that we derived from one of the earlier studies. We used MONAI detection module because we wanted a good adaptation among the community. MONAI is a open source medical imaging libraries developed by NVIDIA, which has many tools that people are using nowadays. And the key question is that, does training with the DLCS improve the performance in the other data set or not? So let me walk you through what is the key results. So we developed 2 models. One model is trained on DLCS, that called DLCS-D detection. And we trained another model on the Luna 16. Luna 16 is a little bit, they have some predefined 10-fold cross-validations. So you have to do that. So we took their model as another model and trained using their same benchmark. So if we look at the Luna 16 benchmark, here are the top 3 models on their benchmark. And when we evaluate our model on their benchmark, our model is almost matches the top 3 models in their benchmark. So this is good. And you can see a very high performances. But don't get misled by these performances. This performance is not what you get it in the real world. The reason Luna 16 has a very high performances, they have an exclusion criteria in their evaluation where you exclude most of the confusing false positive detection. That's why you get such a high performances. So this is you have to be very careful when you find this performance and replicate. So then we went and evaluated our model on NLST 3D, which would be external for both of them. And what we have seen, this is the performance of Luna 16 detection model. And this is the detection performance of our model that we developed. The same model, same configuration, just we have changed the data. And you can see our performance, the performance of our model is comparatively better. And what we can see that training on DLCS can improve detection performances. So the next thing is the classification benchmark. So for the classification benchmark, what we did actually, the task is to giving a nodule 3D box of a 64 cube patch. We want to do the classification, is it cancer or no cancer? We train the model, all the model, we have multiple models. I will walk you through this. We have trained all of this model with the same configuration with DLCS, and we evaluated on the external Luna 16, NLST 3D, and Luna 25. Let me go you through with the models that we have did. So first, we trained with the ResNet 50, which is ResNet 50 randomly initialized. Then we took 2 of the very famous pre-trained Model Genesis and MedNet 3D. They are also ResNet 50, but trained with very different kind of self-supervised learning, this kind of pre-training they did. We used one foundational model that called foundational model cancer biomarker that is trained on roughly 6,000 to 8,000 CT nodules. This is also a ResNet 50, but what they did, the ResNet 50 as a feature extractor, you give in a nodule like box, it extracts the features from the nodules, and then you train a linear model to do the classification. And then finally, we propose one of our pre-training that we call strategic warm start. Let me just walk you quickly what is actually that. And the main questions of this study is that how much well do the nodule risk transfer happens if we train a model with DLCS, how well it generalizes with other data sets. So for warm start, strategic warm start, we basically have 3 steps. The first step, we actually get the pre-training data set, and how we get it, we ran our detection model on DLCS. We get the false positive patches under different confidence, low to high. Once we have all these patches, we combine them with the real nodule patches and false positive patches, and we train a ResNet 50 for false positive reduction. And once this model has trained, we have passed this weight to train a new ResNet 50 with this training weight as a pre-training weight for do the lung cancer classification. The reason we went through that is that rather than starting from a random initialization, we wanted to learn the appearances of the nodule or get used to with the anatomy of a CT. So let's look at the performances. How does it look like? So just to remind you, the task was to do benign versus malignant classification. And this is the sort of the performance that we got. And you can see that our pre-training is matching or outperforming the foundational and pre-training models. But what is more interesting here to see is that the performance difference between Luna 16 and Luna 25. You can see for Luna 25, which has a follow-up and pathology-driven results, we have 80 AOC for our model here. But for Luna 16, which is visual scoring, here we have 90 AOC. So you can guess when you get the score from visual scoring, it might be easier for the model also to distinguish between cancer to no cancer compared to when you have real pathology driven or follow-up results for a nodule being cancer or no cancer. So I think the main takeaway from this chapter is that there is very less availability of the public data sets out there for lung cancer diagnosis. So we try to develop one, and we try to evaluate it under different task, detection, and classification, and how this performance actually goes on the other external data sets. And pre-training, the approach that we said, where you don't need any additional data, but just train it to get used to with the anatomy that you have in the CT or the lesions that you are trying to classify will help. So the performance, the main takeaway, I think, the performance differences you see in the models, there are two dominating factors: the data set you are training your model and the reference standard you are evaluating. So that are the very two factors that you should always be careful when you're evaluating such model.
Sure. Question.
Yes.
Before you did the study, can you comment on, or even now, what is the understanding in the field for this take-home message? Like, I mean, I think when you say it like this, I think most people would say, well, of course, that seems kind of obvious. But was it obvious to other people who are doing lung nodule detection or classification? Was there any discussion about, oh, I'm using Luna 16, and so please take my results with a grain of salt. These are probably optimistic for the following reasons?
Yes, so I think the problem is that, like, in the field, when we starting for lung cancer classification, especially, the performance we see in most of the studies, they're in 90s. But when we actually go and use our model on like actionable data set like DLCS, we get the performance around 70s or 75, which seems like, are we doing something wrong? Or something is wrong with the data, or something is wrong with the field? So I think there are multiple factors we have to consider as a community for lung cancer detection or diagnosis. The performance that we are reporting, we have to be very careful of the reference standard that we are using. If we are using a visual score, I'm not saying it's bad. It might be one of the options that you can get a lot of score without a lot of like biopsy or other study follow-up, but it might be easier to judge a model that what the model you were judging, the performance you see 90 is not realistic in the lung cancer, at least classification. It's a very hard job, and getting a performance in 90s, I will be stopping my research, I guess.
So have you seen, I'm not trying to make you embarrass anybody, but have you seen any papers where they have said something like that, where they have said, because I know maybe as recently as a year ago, I have in this room probably said something like, oh, lung nodule detection is a solved problem. Right? I probably used almost those exact same words. Just a few days ago, somebody else said that to me as well. I didn't correct them at that moment.
Yeah.
But
I think detection never was a problem for lung cancer diagnosis. Is the rate of false positive that you get. that was the biggest problem in the detection.
Mhm.
In the classification, the problem exists. All the models are there. They are not up to the mark in the performance that will match even the radiologists. They are very smart people. They are very skillful, and it's very hard to beat them. You cannot beat them. The thing is that how you can support them. I think that was the idea. And we did one of our work on that. At the best of my knowledge, we are one of the first that were kind of in our benchmark paper, we are pointing out that this performance, you could be very careful when we report this kind of
So this could be
performance.
controversial.
Yes, we can get a lot of, but we showed what we get. We have our models, data, everything out there. Yeah, feel free to use it.
If I follow up on that, I feel like so far you're essentially saying, well, don't take those claims out there as seriously, your problems. So you're coming as a critique of the science that is projected out. Can you be more positive?
Yes.
As a board, if you were to start the company tomorrow, based on what you have learned, what you would do otherwise, so you actually can have better performance. So as opposed to being reactive, how can you be proactive based on what you have learned? That's my question.
Yes, I think what we did in our paper, like rather than being so much critics, what we said is that if you develop a model, your performance will be in this range in this kind of reference standards. So it's again the way we are pushing it. Okay, if you have this reference standard, you should get a like visual scoring might be easier compared to like I would say the nodule classification is one of the hardest job because you have like different lung rat score and like doctors might also get a little bit confused sometimes to judge it a cancer or no cancer. That's why you have follow-ups and other rules. So I think it will be a way of telling that okay, you should report the performance on this reference standard and report the performance, how your performance will be on a biopsy proven data, on a visual scoring data. I think that would be the way of pushing any device or something. Say.
I like that kind of spin. So basically, instead of criticizing, you can say, you can invite.
Yes.
So if you now have this resource, you can say, we have put out a really good data set and a really good performance benchmark. And so your company X, you should look at
Yes.
it this way. Don't go using the Luna. Well, okay, then it's not that
Yeah.
criticism.
No, but don't get me wrong. Luna 16 was one of the first people they have released the data, which has inspired all this research and study. But it's a way of annotations. I would not say this is bad. I'm saying you just be careful when you report such a high performance.
Have you sequestered any of the data?
Sure.
Have you sequestered any of the data? Is the data all out there?
Yes, it's all. So we have released 1,600 of this volume out there. 500, around 400, we kept it as a complete test set.
Good, excellent.
That we are not sharing with any other people. Anybody want to evaluate the real like performances? Yeah.
You haven't even touched it yet.
I haven't even touched it yet.
So
This is not even it's like I developed it, but I don't even touch it yet.
You leave the lab, I need to know where you hid it. Nobody would.
That's very important.
Yes.
Of course, we always need to be careful offboarding, but in this case, we launched it with so.
Yes.
You didn't even see it.
I didn't even see it. Yeah.
We took that to extreme.
Yeah.
Yeah.
So the next thing of this chapter is that so far all the models I have shown you, they are sort of fragmented. You can do detection or you can do the classification, but you can go over a step. For classification, you need to extract the patch. For detection, you need a CT. But can you unify all these things that we have developed so far? And can it be just one go model or one go tool that can be useful for maybe detection, annotating data, or what do you want to use it? So that we call it tri-reader. It's a 3-stage consensus-based AI model that can do all the steps that I have shown you so far. Additionally, it has few other features. So let me walk you through that. So in the workflow of radiology, you can see there might be multiple steps. You do detect, you do characterize, and you do refinement. And it might be also very important in lung cancer detection that in many of the time you get annotated only for the actionables one. But what about the other annotations that you may have? So that is also one thing that we wanted to explore. So that's why we proposed this model. It's a 3-stage AI framework. Let me walk you through it. It might be easier. It's a very complicated diagram, so I will not go into so much deep, but I'll try to convey the main message. So how does it work? Given a CT scan, it has basically 3 steps. It first is a candidate proposal step, then you have a malignancy risk score step, and then finally you have another final refinement step. So how does it work? Given a CT scan, completely you don't have to do any pre-processing, nothing. You just feed it to this input pipeline. It will go through 2 detection model. So here we have 2 detection model. One detection model is detect everything, false positive, true positive, and everything. The next detection model actually detect most actionable one, which they think like very suspicious one to detect for as a nodule candidate. If both of them agreed, we pass this candidate as a probable candidate for our annotations or reading any study. If they're not agreed, it passed through a second step where we have 2 classifier 1 and classifier 2. This 2 classifier has been trained with 2 different data distribution. One is DLCS 24, the other one is Luna 25. We wanted to give them the perspective of both of the world. If data shift or data distribution shift, how the performance or risk, by risk score, I mean what is the probability of that candidate being cancer or no cancer. If both of them agreed on a certain threshold, we keep that candidate. If they are not agreed, it go through a next step, which is this very third one, where we're trying to find out the locations of this candidate. So what happens sometimes, we do get a lot of false positive detection from our detection model, and they might be not even nodule. They can be outside, they can be somewhere like liver nodule or some other nodule. So you want to constrain that to be found in the chest and pleura area. So we find out the locations, segmentations. You can do also some morphology operations. There are options, but we're not using it right now. After you get these locations, then you do a final refinement between these 2 detector, is the earlier detector. If they agreed, if they are like having certain threshold of being a candidate, we keep it. Otherwise, we reject all those candidates. Now you can ask me like why you are doing so much this complicated work to getting annotations or detections. I can show you the impact of this study. So one of the very good part of this tri-reader study is that here you can see the performance on an external data set, which is Indomix. It has roughly 2,000 CTs, and each of the CTs has 1 nodule annotated in it. And here I'm showing you the sensitivity at the 1 false positive per scan, which is for Luna 16 detection model is 0.66, for DLCS is 0.78, and for tri-reader is 0.8. So it can sustain the same level of sensitivity. But what is interesting, here you can see the number of candidates it detected. It can reduce the number of false positive by almost 2 times, sustaining the sensitivity of the model performances. So I think here it gives the benefit compared to other earlier single fragmented model. Yes.
Yeah, asking one question.
Yes.
So explain this to me. I was under the impression that when you use a deep learning type of algorithm, there are so many layers already built into this infrastructure that can essentially is not a single reader, is actually a variety of readers all joining together to try to come up with a decision. So if that is the case, why 3 of them together should do better than 1 of them? Any of them would be a compilation of multiple series of network, layers of network that are supposed to be, in other words, 10 of these or 1 of them, they should perform equivalently.
That is one of the way of thinking it, but
Yeah.
the way we propose this project is that we are narrowing down the search space for each of this model. So you
They have specialized in a different task.
Yes. Yes. So we are like, if you see the first detection model is seeing the whole city. The next classifiers model is only seeing the candidates they are not agreed on, or you're already reduced your whole city space to a candidate space. So we are narrowing down the task in each step. So
But can it be done already in a context of a singular AI algorithm with its different loss functions and so on?
it can done, and to be say you that in our detection model, we do already have those mechanisms.
Yeah.
It detect, and then we do bounding box regression, give the probability, but it was not good enough because you're getting a lot of false positive.
So you don't know why. You're saying it works, but you don't know why it works.
I think there are two way of I think we sort of knew it, but prove it will be very hard. So one of the problem is that most of the data set out there, even our DLCS data set, we do annotate mostly the actionable nodules. But in the real clinical data set, you could have 10 nodules which are not annotated. And your detection model will be finding those nodules if you're training it to find a nodule. So sometimes even you say this is a false positive candidate, but it is a nodule. So it's a very like repeated thing to evaluate on. So that's why we're trying to narrowing down the space in terms of we don't miss the candidate, but we also don't miss the candidate which has the risk of cancer later. So that is also very important, right? We might get the most actionable one, but what I'm trying to say, maybe this will be clear if I show you this figure, right? So I can zoom it a little bit. So for example, in this data set, we just have annotations for only this nodule in this data set. But what my model is telling you is that, okay, this is the one you have annotated, but see, the risk of that candidate being cancer, you have this risk bar. So maybe also look at this candidates that is not annotated, but you should look at because it has a very high risk of is a very high risk of cancer. So this was one of the way of like narrowing down your space and not maybe missing it, being consistent and giving you also the, you can say it like prioritizing what you should be prioritizing, what is like most significant here, the other candidates. So that is one of a way of doing it.
Some thoughts about this.
Yeah, well, I'm just very briefly, so
Yes.
what would it take, if somehow your job was to come up with one model
Yes.
that could do it all, how would you do that? Could you come up with a model that would do all the tasks to find all the nodules, to pick out the most risky ones, to give it a believable malignancy score? What would that take? Is that doable?
It's doable, but that model will be more complicated than these individual models. Because now you can see before that model was trained for one task, but now it has to consider multiple tasks. And then you have a redundant layer of loss functions, right? You have to optimize the weight for each of these tasks separately. So that was also one thing that when you have a chest issue, you go to a chest radiologist, maybe a chest specialized one, the doctor. So it's sort of like you have a specialized model for each of this step and maybe use that one. So that is one of the thinking of TriReader. And the good part about it, you have a better model tomorrow, just replace that model. You don't have to replace the entire workflow.
Yeah, the module.
Yes, so that is one of the good part. You have a third model classifier tomorrow, fit it in. So that is one of the good part about this modular approach. You don't have to train the whole thing end to end. And you can also add, like we recently, I did add the radiomics features also to this module. So you can also get everything end to end.
How many cases get picked up in each step?
So if I show you like majority of the cases get picked up in the first step, the rest is like you get like half and half in each of the steps. Yeah.
It should become small.
Yeah, this becomes the narrow down the search.
I think I found what's going on there. Wait, correct me if I'm wrong.
Somebody is.
Yeah.
If your candidates are for a test set, right? Like that you will later annotate, or are you annotating now with the AI tool?
You can do both, right? You can do both. And the other thing that we do with this approach is that we do individual score for each of the STAFE candidates. So later on, if you want to train a specialized model, which will find each of this special kind of candidate, you can also filter your annotations that what kind of annotations you want. You want the only full confident one, or you also want which has like half of confidence. So you can do both with this kind of approach.
So from a branding point of view, he originally called this try annotate. I'm thinking you can do that. I mean, if your goal is just to take a lot of data and generate very high quality annotations, medium quality, low quality, that's one thing. But I was thinking it's also kind of cool because there's different kinds of readers Maybe that's a little too
Yeah.
close to the CBIT lingo.
The reason I
Yeah.
called it the annotate because I used this model to annotate roughly 6,000 new cases from NLST and 5,000 other cases that we had at Duke lung cancer screening dataset that we haven't released. So we are working on that to enrich that dataset using this kind of approach where we have the confidence for each of the annotations, how confident we are. Rather than making a math student doing all this hard work, we are trying to customize that approach. So this is one of the goals. Yes. Yes. Yes.
So they make it all the way to the end, they are almost certainly false positives or just really poor quality stuff at that point.
Yes.
But they're still there. I mean, if your algorithm could benefit from very low quality candidates, you can set
Yeah.
those.
So you can see here we like for each of them. So this report is automatically generated by this model, and it also scored that like 0.5 because it's gathered in the second step. We call it 0.1, 0.5, 0.25, and 0. And it also gives the locations and all these other things. Yes.
Okay.
Yes.
So to reiterate one of the questions, like in order, like for you use 3 stages to do it, and what would be the reason why you don't do it in one stage? Would be cost prohibitive to train a model that big, or like computation data available, or decision boundary hard to play? What would be the reason?
I think the first thing is the computations and optimizing the model. It will be very hard because it will be learning multiple steps.
Yep.
And the second step, the data. Data will be definitely a huge problem doing all that in the one step.
It's a different way of asking.
Different way of- yes.
question. Yeah.
Yes.
So I think I was fishing for that data answer. Okay.
Yes.
Okay, let's keep going for now. And
Yeah, there is a huge series of implications in this. And I would love to talk to you more. I don't want to.
Yeah, yeah.
Right.
It has to do with what is our vision of intelligence, of the form intelligence. So the
Yeah.
fact that it says some specialization in medicine is no accident. You're essentially replicating the same processes.
Right.
And we're recognizing that any form of intelligence is subject to other.
Yeah.
And noise, and therefore you're trying to minimize that. It's an optimization problem.
Even the first stage, right? Even the simplest stage of all, just the detection, he's already got 2. You could just argue right there in stage 1, why do you have 2? Why not 1? Right? I mean, they're literally both doing detection.
Yes.
In fact, they're literally the same architecture,
Yeah.
same data, you're just using 2 different operating points, if I recall.
So in the second model, we did also added the confidence data in it so that we can get the both perspective, what is a candidate and what is a false positive candidate. So there is a lot of practical experience that we gather from all this work we put into this model. So scientifically, I think there are many approaches of doing it, but that approach, I find it most practical in terms of the experience that I had.
Let's talk about.
Yeah, yeah.
Yes, sure. Yes.
Okay, let's keep going.
Yeah.
We've got 2
So,
more chapters.
Yeah, so I think now we'll talk about an interesting chapter. All of us interesting,
It
but
gets
this is
more complicated.
yes. So here you can see an image that we generated from ChatGPT. Dr. Low generated it first, then I copied the prompt, and then I added me here. Yeah. So now you can see I asked it to add me there, giving my pictures and keep the nodules here. But generative models has been very advanced over the years. We can see a lot of output in the image generation and video generations. But what is the state of the radiology in terms of generative AI? How we can maybe utilize, or what is the state, how people are using it right now? So seeing such a success in the natural images and video processing, there are a number of groups who have started applying this kind of generative diffusion model in CT generations. And some of the groups have shown very nice performance. So one of the group is proposed, like MICE is from NVIDIA Medical Imaging Research Group. So what they had is that it's a very famous model. So you have the 3 different components in this model. You have a feature extract, you have a VAE, then you have a diffusion model, and you have a control net. So far, all these models, they're good at producing a CT image. Global anatomy wise, they might look good. Not going into the physics, but visual wise, they're good. But the problem with this generic CT diffusion model is that they misses smaller nodules, and many times they misses lot of nodules, which is the most interested for my task for lung cancer detection, diagnosis, or classifications. So here, suppose here is an example that we have a CT scan. So how this model work, you can give a mask of body, organs, and nodules, and it should generate a CT using constrained by this segmentation mask. So what we find out when we applied this model, it misses the nodule, which might be not helpful in our task. Here you can see this is, it should generate a nodule here, but it's missing the nodule here. So we find out that there, and this is not the only one example, there are multiple inference that we went through, and is the case for smaller nodule especially. So yes.
You asked it to generate a nodule and it just refused?
No, so what it does work, like you feed a segmentation mask, and the segmentation mask will be having body, your organ mask, and the nodule mask that you want it to generate in that
So you
CT.
did tell it, I wanted.
Yes, I wanted it, but
And it just didn't.
yeah, it missed it. So what we realized that it might be not problem with the model, but it much has to do with the data they have trained with. They have trained with a large amount of CT data, but what they miss on, they haven't fitted enough nodule data. They just had roughly, I think, 50 or 60 nodule data there, or like maybe 200 from the same sources, which is not enough to make a generative model for lung nodule. So we find there is a scope that we can make a generative model which will be nodule oriented for our task. So when we went to solve this problem, we proposed NOD-MICE. It's a nodule-oriented medical AI for synthetic imaging. And some of the out of product for this project is that we released few of the open access libraries where you can do context-aware nodule augmentations, and you can do segmentation of the nodule depending on the points that you have. So let me walk you through what we actually did in this project. First of all, what we did, we saw there's a problem with this model from the data perspective. So we aggregated a large data set, where this data set, we combine all the existing available lung cancer data we could get. We combine them data into CT, get the segmentation mask and the nodule mask. Then we trained a diffusion model and add a control net so that we can control the generations constraining the nodules in it. And then we propose a augmentation technique. So once you have this generative pipeline, what you will do, you can enrich your existing data set with sort of augmentation so that you can give the variability appearance in your data. And finally, the main question is that doing all this hard work, does it really help in your downstream task? So we try to evaluate it. So here's like basically walkway. So let me just show you what we did actually. So here's the data set that we built up. After combining all different data set, we come up with 14,000 nodule from roughly 9,000 CT scans from 8,000 patients. So this is as far as we know, this is one of the largest data that we have concatenated in the lung cancer study. And for each of these data set come up with different reference standards. Some has the bounding boxes, some has the segmentations of the nodule, and most of them doesn't has any body segmentation mask. So we have to go through a multi-step process to get all of that. So what we did actually, we used a deep learning based so here is for example, here's a CT scan. We used a deep learning based segmentation model to get the segmentation of the organs. Then we did some image processing to get the body segmentations. That deep learning model was not segmenting the body. And then after doing that, the tool that we developed, it called spins. Given a point of the nodule, it can segment the nodules. So we have segmented the nodule for this, the entire data set. After doing all that, for each of the CT scan, what we have a CT scan, associated organ and nodule segmented. After we have all that, we went to training that model. So apart from training it from the scratch, what we did, the foundational building blocks that NVIDIA has already provided, we started from that point. We use their VAE to, so by default, CT scans are very big. So computationally, it becomes very expensive. So how we have used this VAE is that they also propose that we, from the CT embedding, we put it to a latent space so that the computationally it will be less expensive when we're working with the whole CT. And then afterward, we train the control net fitting it the constraint of our body mask, our lesion mask, and the spacing that we want to that CT to be generated. It will be, I think, more clear when I will show you actually the building blocks. So what we had is that having a CT scan, we use the VAE and it transferred the CT scan to a latent space here. And using this latent space, what we did, we fitted to their diffusion model, flow-based diffusion model they have. And this model gets basically those latent space, and we can give the spacing that we want the CT to be generated. Afterward, we feed our body segmentation mask with the nodule mask to this condition control net. It feed those conditions to this diffusion model using cross attention. And then finally, we train this model using a region-specific constructive loss. So what this loss is doing actually is trying to force the model to generate the nodules by giving it differences between what is the background and foreground. It might be getting very complicated. So let me show you after we've done all this training, what we have this model. So giving a voxel spacing for the CT you want, you can give a segmentation mask to it, and it will generate you an CT scan with the nodule that you want here. See the nodule? It's basically the same case where we missed it earlier, we can get it now. So now we have seen that I have shown you that we can generate now the nodules giving a segmentation mask of the nodule that we want and the body constraint and the spacing that we want. So how are we going to evaluate it? So we try to evaluate it doing two approaches. First, what are the clinical data we had? We generate the digital twin of that exact clinical data using this pipeline. So we get the segmentation mask of the body and the nodule from those clinical data, and we used our approach to generate the CT scan. And then we did two kind of evaluation. So we did FID, which is basically try to compute the distance between your data 1 and data 2. So we evaluated based on our real data and the AI generated data that we have. And the next thing, which is more interesting, that we try to evaluate the detectability of these nodules using our tri-reader high sensitivity model, that how well this generated data is detected by the AI readers. So here you can see a performance on the detectability. What we did, we evaluate the same clinical data with this model. We get the same data using the MyC model and using our model. Here you can see the performances. Our model performances is closer to the clinical data. Clinical data was in the blue one, and the FROC, that our one is purple. And the MyC version 2 is actually here. Why is the reason that performance is so bad? What the point I have mentioned you earlier, it does misses a lot of smaller nodules. And we checked that size bucket FROC, and we also did some visual checking that how does it going actually. So here you can see two examples. Given this CT as an input, it should generate a nodule here, but MyC version 2 is most of the time missing the nodule. If there is no nodule, there will be no detection. That's why the detection FROC was so bad. So yeah, so this is. So now I've shown you that we have this pipeline. We can generate the CT scan using the segmentation mask with a nodule or the body that we want the constraint on. Now, what is the usability? How we can, is it really works in the downstream task? So for that, we took over a classification task that we want to use this AI generated CT, add it with the real clinical data and see if that helps. So now making the same clinical data, I don't think so will be so helpful. So what we did, we actually made some augmentations. So what we did, whatever the clinical data and the segmentation mask of the nodule we have erode, like do some image processing, image processing operations. We shrink that nodule mask so that we can get an appearance of the longitudinal data into our data. So keeping the body and everything same. We are just changing the appearance of the nodule sizes so we can give a variability in the data. So here you can see the original nodule distribution from Luna 16, Luna 25 training data we have. The mean is 17. And when we do this augmentations on the nodule mass, our mean shifted to 13 millimeters. So we are trying to enrich our training data for that. So once we have this augmentation, we generated our CTs using that synthetic pipeline. Now, how we did the classification work. What we did, the classification was giving a 3D bounding box of the nodule. We're trying to classify cancer versus no cancer. We used ResNet 50, a very simple model, because all we are trying to do is that we're trying to understand the implication of the data. We did multiple study on the regime of the training data. We reduced the training data at 50%, 20%, and 10% to simulate the effect of low data resources. And then we compare basically 3 approaches. First, we just train a model on the clinical data, Luna 25. Then we train a second data where we added the real data plus MICE version 2 model, augmented synthetic data. And finally, we added real data to our the model that we have generated the data. And here you can see the statistics of the development set and the external data set that we have tested the model on. So let's look at the results. I forget to animate it. So here, let me walk you through this performance. It will be easier. So first, what you have here is the performance for the clinical model when you train that model with only Luna 25 clinical data. Here, the x-axis is basically the percentage of data we are using. We are using 100% of the data. We have sampled the data at 50%. We have sampled the data 20% and 10%. And this is not a single sample. We actually did 10-fold cross same fold, and we basically reporting the mean performance. So after we have that, this is the clinical model. Then, so now this is the performance from when we add the clinical data with the synthetic data with the MICE version 2, that other model. Now, what's the performance on our data? If we add our model, and here what we're doing is that this n percentage mean, whatever the 10% of the real data is here, we are adding only that patient there, only 10% of the synthetic data here. So we see that the performance when slightly is not that beneficial. But what if with this 10% data, we can add all 100% synthetic data? We can enrich the data a lot. So that's where I think the magic begins. You can see the performance jump. You might get almost very similar performance where you would get with the 50% and 10% of the data. This is with the MICE, where they miss MICE version 2, miss many of the smaller nodules. And with our model, we can get the performance even a little higher because we do generate a lot of the smaller models. And it's also true for other performances. Here you can see. So we also tested on other models, and the trend is similar for that. So what we can see that when you have a lot of real clinical data, adding synthetic data will not help. But the moment you have low data resources, especially 10 or 20% of the data, this synthetic data can add good value to your model performances.
How many synthetic data?
So it's like the clinical data was like 25,000. So we sent it, like when we say 100%, all 25,000 was.
So isn't that just the fact that you have more data? I mean, assuming synthetic data have similar quality.
Yes.
Data, which it doesn't exactly, but if that is the case, you're demonstrating if I have more data, I get better results.
It's not only the more data, it's also the variance of the data that we are introducing by augmenting the nodules in it. So you can imagine Luna 25 have one patient, one nodule type. For that patient, what I'm trying to do is that I'm shrinking that nodule and I'm giving it a longitudinal data, which might introduce more variance and understanding of the nodule.
Assuming you have modeled your synthetic data to replicate the diversity of clinical data.
Yes.
You're demonstrating that essentially you could get away with having less clinical data and have as many synthetic data to accomplish something.
Yes. So I think last but not the least, I think I'll try to wrap this up very quickly. So far I have seen you all like how we can do weak supervision and synthetic data classification and all that. But what about the virtual imaging trial that I showed you in the earlier? Can you use this data to train our AI models? Yes, we can. So here is a very short slide that, so you remember the nodules that we have generated in our earlier VLST study. So what we did, we actually used those nodules and added to clinical data, which is like MAT604. It's a 60 annotated nodule, like most of the people use for lung cancer nodule segmentations. So we used that data and added our simulated data from VIT to train segmentation model. And we trained basically multiple segmentation model where we compare between, it might be easier here. We used, trained a model with only clinical data. We added the clinical data plus simulated. And we also trained another UNet model with clinical only and clinical plus simulated. And here you can see adding simulated data to the training has always improved the performances. And this performance improvement is much more when you in the sub-centimeter nodule. Here you can see the performance, and all this performance are the external test set. And here you can see when we added our simulated data to our model training with the real clinical data, we get much higher performance, especially for the smaller nodule representation cases. Here is one example. I think this is visually nice to see. Yeah. So as I have promised that I'll show you this comic that I presented in VITM. So this is not a comic. It actually tells you a very nice problem that VITs has. So here, this Superman is basically a VLST Superman. And this is a nodule in the lungs. It's telling you can detect me, but you cannot diagnose me. The reason is that when we simulate a nodule, we can give it a cancer labels, but is it driven by clinical analysis or some model? Is not. At least in our first study, we haven't done it. It does replicate certain specularity, certain size, certain location. You can do that. But in that study, we haven't done that. Maybe we can do it more rigorously. For VITM, what I proposed that I went to clinical trials that like NLST and Nielsen, and we find out that there are a few models based on only on the size of the nodule. It can give you a label that what is the confidence of that nodule being cancer or no cancer. So you use that we call it statistical labeling, and we just fit the size of the nodule that we have simulated and get a label being cancer and no cancer. Now, where in VITs that we can only detect, now using this statistical label, we can actually give it a classification label and do the downstream classification task. Now, you can question me that why just only size? It's not the only, it may be the most dominating factor, but it's not the only dominating factor in the lung cancer classification, detection, or analysis. So then we went to a study that I call it VLST2, an in silico virtual lung cancer screening cohort derived from the real clinical cohort. So what I mean by that, so for doing that, we went to Duke. We took 500 male and 500 female patients. We used our XCAT toolkit and we get our virtual populations. But here the interesting thing happens. For the nodules, before we replicated a distribution from NLST, but here what I did actually, I went to NLST and I go through all their statistics and finding, we find out that there are approximately 900 primary lung cancer patients in whole NLST. And each of this patient has at least one cancer nodule, which is annotated as a primary lung cancer. So we took all these nodules and we know the locations of this nodule, size of this nodule, type of this nodule, specularity, and does this patient has emphysema or not. So we also, from these cancer patients, we did have also annotated other nodules which are not primary lung cancer nodules. And then we went to other patients where you get 26,000 benign nodules. You might say that why this number is odd, because I was trying to make 5,000 simulated nodules. So I took like 5,000 nodules. If you combine all these numbers, there are 5,000. So then what we did for our virtual populations, the virtual population derived from a real clinical patients. For each of this patient, we have a gender and age. For each of these nodules that we took from NLST, the descriptor, they also have an age and gender. So we try to get the closest match possible between these two distribution so that we can influence that, okay, if this patient has a cancer nodule and his age is like 50, then I go through my virtual populations and try to match the closest, maybe 49 I have or 50 I have, then I take it. If 49, then is basically the closest match. So once we have fixed that virtual populations, we fitted, using this nodule features, we actually generated exactly size, locations, type, is a ground glass, solid or subsolid, and is specularity or emphysema or not. So now we can feed that exact. So now we can say that the nodules that we have simulated in these virtual patients, they have a clinical grounding because they are from a clinical trial. And after doing all this, we get 5,000 positive patients with all the nodules from positive cases. And then we have 500 negative patients with all the nodules with the negative nodules. But that is not enough. So I can say that I have so far simulated nodules based on the real clinical trial populations. But how I'm going to give the statistical label to this thing? So then we come up with this new approach where we use multiple models that has been proven to be effective earlier in different trials, like PanCan. PanCan is a Canadian lung cancer screening risk predictor where you can give this predictions or feature of a nodule, and it can give you a probability of that nodule being cancer or no cancer. We did multiple variants of this PanCan. What we did actually, if you use all these features, is basically PanCan, but you can also reduce certain of the features like family history. I don't know how much we are replicating the family history in our virtual populations. So we can avoid that. We can go with this age, gender, and this features. If you don't even care about the age and gender, you can just go with the variance of model where you just have the nodule features. Now, once you have this kind of model, the virtual populations you have, the nodules you have generated, you can get a statistical label for these patients. So now we can say that the virtual populations we have, this 1,000 simulated virtual populations, the nodules are grounded from a clinical trial, and they can be used in many different kind of next VLST2 virtual lung cancer screening trial. So I think that brings me to the end of my presentation. I want to just conclude saying what we did actually. So first, I introduced that weak supervision that we did. We could have scaled up the data using this weak supervision. And we are one of the first that did it for the multi-organ, multi-disease classification. We built one of the first virtual lung cancer screening trial that can emulate certain aspect of national lung cancer screening. We released one of the modern largest lung cancer screening data set and a open access reproducible public benchmark. And we introduced a generative model that can be used for different lung cancer analysis tasks. We used simulated nodule. We are one of the first to use our VIT's unique resource to simulate nodules and use it in a lung cancer segmentation task. And finally, the new cohort that we propose has its grounded in the clinical and maybe will create the next VLST2. Thank you so much. I thank everyone for being here and all my committee, my family, and all my collaborators and lab members. Thank you so much.
So at this point, I would like to give the committee priority in terms of asking questions. You can do it here in open, or later we can also use the peanut gallery and really pummel him in private, your choice. And then after that, the committee questions, we can also open it up, and we really have a few from great people in the audience. Thank you for that. So committee members, any questions? Go ahead.
Oh, well, I have 4 questions written down. I don't want to dominate, so maybe I'll just ask mine.
I won. 2.
Okay. So the tri-reader, can you, Did you ever go and analyze like where these models are disagreeing? Because the whole pathway, revolves around disagreement. So do you know like where the weaknesses and strengths are of the different models?
Yeah, so one thing I've realized with the, if I talk about the second step, where the classification scores are coming, for the model that I've trained with Luna 25, is basically miss smaller nodules a lot. And it might be due to the data because they're derived from NLST, and NLST has a very strict criteria which one should be annotated or not. So there we have seen a sort of disagreement, but we haven't quantified that yet, that how much we are like their disagreement. The other thing in the detection thing that we have seen, many of the disagreements are coming from with very large nodules. So in our cases, what we do, we don't actually consider any nodule larger than 30 millimeter as a nodule, because that becomes a mass. So there are like few disagreements we have on that. So one model thing is not a nodule because it has not trained to judge as a nodule. Yeah. So there.
Okay, but so this is like a general characterization, but did you like, is that uniformly what's going on, or did you actually go and look at, because if you know what's going on, if you know that this model is really bad for like small nodules, you can fix that model.
Yes, it's not completely unified that is always failing, but mostly it's failing. So yes, we can maybe that is one approach that we can fix that model, or maybe add a new model with training it with NLST plus DLCS. We can combine both so that you see the bold one. Yeah, there is a.
Because like also if you know that like this model is really bad for small nodules and this model detects something and it's a small nodule, maybe you should listen to that one and not this one.
Yes.
So
Yeah,
you
then
can do
maybe
better
you can
than
do
just the
some
majority, but-
weighting criteria also there to add a meta model or something.
Yeah. Okay, well, I have the floor. I will go ask one of the other ones. Did you look at the size of these, the size of the lesions over time ever?
No, that thing,
Okay.
that thing, we haven't done any longitudinal study yet.
Okay, I will yield the floor for now.
One of the reasons that we haven't done it, that the data set that we have in the DLCS, we just have one time point for each of the patients annotated. We try to look at in the NLST, but the annotations we got, the number become very small. Like for the patients in NLST, for the cancers one, only roughly 300 patients has all 3 time points. So that data is very narrow. So that's why one of the reasons that we haven't done it. But with this NodMyC, we think that, or like our VLST, maybe there is an option that we can do it with simulated.
Okay, so I'll yield for now and then I'll ask the other two later.
Sure. Questions?
Yeah. So this kind of spans like everything that you're doing and others are doing. I noticed that like in the CT scans that you show, many of them are the sidedness is different. Like, the sidedness is like the left is right and right is left in the way that we look at them. And I noticed them kind of both ways. When you're generating like, through the VLST or, putting in your own, is there a standardization there? It seems like that wouldn't matter, but it could matter depending on what you're looking at and what others are looking at.
Yeah. So like on the view side, we don't we can control.
Or even the way they're generated, right? Are they generated in a way?
But so the generation has don't have any constraint over it. If you want another view, it will generate that. So view wise, it doesn't. It can be upside down. Whatever the mask you will give for the NodMyC, it will generate in that way. If you give them a left LAR or right LAR, it will generate that way. Yeah, so we don't have that constraint that we want this orientation. Whatever the mask you will provide, it will generate into that view.
Okay.
Yeah, and the other thing that we did is that we haven't, so many of the data set that we worked with in that data is that some come into this orientation, come into that other orientation. We haven't harmonized that because we want to model to learn all the representation. But that is also one thing that we can do the standardization. With our VIT, we can define like which orientation we want the data with.
Yeah.
Yes.
And I guess it's mainly a problem with the virtual, when you're making up these virtual patients, right? Like, is everything being fed such that a patient's left is actually the patient's left, or is there's
I wonder-
heterogeneity?
Yeah, I'd love to know which. So you saw some left-right mirroring.
Yes,
All the time.
yeah.
I'm sure.
Probably
I
at least
think
5
there are
or
a few
6
because like
times.
I
didn't
haven't
catch
changed
that,
the
yeah.
whatever the raw data. I feed the raw data, but that is one thing that we can see if that affects.
Interesting. Okay.
And I'm curious with that, like, the Luna and all, when you get to all these other ones, are they doing that too? Or is somebody missing that? And then things are I'm just curious, like, what the standardization is out there. 'Cause it seems not.
Yeah,
At
but
least for the way
actually,
it's presented.
yes,
Is that a bug or a feature? Yeah.
Yeah.
Many of the data sets have very different orientation. I would say when you work on the segmentation work, that get very highly affected by that. I can say that classification, detection, they may not that much, but in the segmentation, we have seen that effect a lot. If you train a segmentation model with one orientation, and if you give it some other orientation, it does affect. So yeah, that is one thing that we have seen so far.
I guess I'll one follow-up question. So like, you know, in all of these different studies that you're doing, you know, specifically the tri-reader, like the nodules that are, you know, likely a false positive, are you going back to those in any kind of manual form and having somebody look at them and be like, why is this bad? Like as far as a radiologist or even not a radiologist, of like trying to figure those out deeper. Sort of like a spot checking these bigger data sets.
We haven't done it, but if you remember the image that I have here, this basically the report that I'm trying to generate is basically sort of a kind of a reader study, so that they can go with like this kind of thing. This report, that model generate this kind of report, 1 page. We can define how many candidates it can give. So currently it's like 10 candidates. So this kind of report we are generating, so that kind of reader study, so that we can actually know what is going on. So that haven't done yet, but we have a plan to.
But it brings up the question too, like when do we accept that these things are good enough to just let loose, and when do we continue spot checking them, I guess?
I think like, so with the one, I would say like it has 3 stages. And the first, whatever the nodules that has cleared in the first stage, we might not have to look at, because this is like mostly they're very good. Second stage, I would say they can still be considerable because they're best on the risk of cancer. So maybe you should consider it. Whatever is getting on the third stage, I think that cross-checking that part would be most interesting. And we might also want to train a later, suppose release the data. If without any human labor, we can define the quality of the annotation based on this course, that we think this is the most confident annotations and this is not.
That would be a new thing though, right? Because I think most data sets don't offer any kind of confidence or anything like that.
No, there are a few chest X-ray, but not like in that granular label. It's basically rule-based algorithm. It says like just rules from chest, but not in the image base that we did. There's not.
Dr. Smith, Dr. Gong.
So you have done a lot of variety of works using clinical data, releasing clinical data, releasing good labeled clinical data, created synthetic data, demonstrated that synthetic data can well amplify, accommodate, or augment clinical data. And you have done studies with virtual data. So so 2 questions. Number 1, how do you put then the utility of virtual constructions in the development of AI? Seems like that your last task was essentially demonstrating that synthetic data might be good.
Yes.
So do we need to fuss with the virtual data anymore? What utility virtual data would have, right? Number 1. And number 2, I mean, AI is here, and regardless of how good these AUCs are respectable. And I think people are going to start adapting them clinically. There is no question. Whether it's 0.85 or 0.89, people are going to start using them. So what are the takeaways, major takeaways from what you have learned that you want to communicate to the radiology community?
Yeah.
2 questions.
Yes. So on the first question, that utility of the virtual data. So far I've shown you like very different aspect that how we can use our synthetic data, the modern way of doing, and very procedurally generated synthetic simulated data. So one is very keen difference between the synthetic and simulated is that simulated, we do have a lot of control over the data. Like when I say simulated, I can control the size of the nodule, size of the patient, size of the like imaging features of that scanner that I'm simulating. In the synthetic data, I lose many of these controls. Like, so currently the models I had or other models out there, none of them has that image-based control. So you're missing that part. Lesion generations, you can see like how my version 2 has misses a lot of smaller nodules. And I like my model also don't generate all of that. It will fail maybe 10%, 5% of the cases. So there's a failure is a guaranteed. In the simulations, you can avoid all those things. But obviously, there are a few trade-offs like simulations. You need a lot of that tools that is very much unique to centers like very big centers like ours, like CVIT, like the Duke Sim, virtual patients, XCAT tool. As we are sharing this with the public, is becoming more available, but they're very controllable and they're in kind of standard. They are sort of the gold standard of data with no noise, nothing you can do. But there's problem with the computation time. You need large computation. If you have large servers, you can get a lot of data. On the other hand, in the synthetic space, you might lose many of this quality. You may not control physics, you may not control the patient appearances, and many of the time you need a segmentation mask to generate it, segmentation and all that. But what you can do, you can generate a lot of data with compared to shorter amount of time. For example, using MySync, it can generate a CT scan given a mask roughly less than a minute. Less than a minute. So less than a minute, and like it's a big image. It's like you can generate image from 512 cube, and you can also generate image of 64 cube. So
one GPU.
It's need a lot of GPU. It's the 48 GB card that I have used to generate one inferences, but it can generate within 1 minute one CT given like this size. So you can see there's the trade-off, like quality versus quantity, and both has their own trade-off. That's how I see the first questions. In the second question,
Second question, so what's the upshot? The fact that AI is going to be made using the clinical space with or without your work. It's already there, I think. The reason it's not there is not because of the AUC is not high enough. It's because we have not worked out the IT system to get it to work. That's the reason.
Yeah, I think the main point that all my work have showed so far is that performance-wise, AI have a very nice performances, but the main problem that happen most of the time we cannot explain why these performances are. Are you going to give a model doing your diagnosis for cancer without understanding it? That is one of the questions. What my work is trying to do, I'm trying to give you different tools that will evaluate that AI model that will be helping you in diagnostic or detection so that you know the limitations of this thing. And byproduct of this, I'm also giving you different approaches that you can develop this model, evaluate this model, and maybe get out of more refined clinical, simulated, or synthetic data in the task that you are interested.
Cynthia, you can jump in, or yeah.
Sure. Have you ever tried optimizing the data that you're generating so that it maximally gives you accuracy on the, like when you test? So for instance, since you can generate an image in less than a minute, right? Like there's going to be a certain part of the latent space that you're generating that maybe isn't represented. The real data is over, like there's more of the real data than the simulated data. So you want to simulate more data like that, right? So have you ever like tried to optimize that process?
We specifically that process we haven't touched yet, but what I try to do with that loss, I try to make it very optimized for the lesions that I'm trying to get it. So yeah, so for the lesion specific, I do that. I put a lot of weight on my lesion generations. So I try to make the optimize on the lesion side, but other part of the generations like organs or other things, I haven't did that part yet.
But okay, so let me give you an example. So let's say that you have some generated data that you generated, regardless of how you generated it, right? Then you have a subset of real data,
Yes,
and you're using that as a validation set, okay? So then you say, look, I'm not able to detect nodules like this or whatever. Like maybe I should generate some more data like that, so I'm not going to miss those nodules, right? So how do I optimize that data generation to do that? It's like an actor critic model. Like,
oh, okay, yeah, I got it.
Yeah.
We haven't done that part yet, but yeah, I think we can do that. So we know that what are the cases that what I've mentioned that is mostly fail on the smaller cases. So maybe generating more on that smaller side, and maybe the conditions that I'm feeding currently is basically only the conditions of the mask, but maybe I can add some more cross attention to it and say that, okay, this is the type of the nodule.
Yeah.
Because I have that data. This is the size of the nodule, like putting also some other kind of attention to that.
Or
Maybe that,
location or whatever, yeah.
annotations, or I'll do also have bounding boxes. They should not ever cross. I have the segmentation mask, but maybe I can also put a bounding box and say you should never go beyond that, or you should not never like less than that. You have to be, that kind of constraint maybe we can do and try.
Because your augmentation was agnostic to that, right? You said, I'm gonna
Yes.
give you 10%, 20% augmentation.
Yes.
What Dr. Rudin's suggesting is you might be able to give it 10% smart augmentation. You might dial in on the 10 most difficult percent.
Yes.
And simply by giving that, that might be all it needs to jump up performance.
Yeah.
That's really clever. I like that. Yeah. Okay. Any other questions?
Interesting. I mean, one other thing is just like the fact that in the original Macy formation, the nodule was not put in.
Mhm.
By what you did, essentially you accentuated that for the network to say, actually, I really care about that little tiny thing over there. Don't miscreate in that. Don't congratulate yourself saying, I got the main gesture off. I'm actually interested in just this little part of it, right? So somehow accentuating what we want out of our AI agents is actually part of our task. In fact, all of this AI training right now, people are doing that, like how to accentuate, how to ask the right question, as opposed to just asking a question. So how you orient it.
It's a version of what Cynthia was saying, because they're very proud. This is NVIDIA, by the way, to create this thing, right? So infinite resources, infinite money. They train on 50,000 CPs.
30,000 CTs.
Yeah, it's probably the large. They basically scarfed up every CT on the
other problem with their model is that you kind of test it out there because they use all the available CT data.
That's right. So every data set out there has been used for
The
training,
only thing they don't
except ours, because ours was not out at that
but
moment.
they do have all the available data.
Yeah.
So testing that model is another very big issue.
Yeah. But the problem is that they didn't think about what was the right data to use. They simply just sucked up everything they could, just brute forced it. And so even though they have the constraint for the nodule, it failed anyway. And he didn't change that constraint. He simply said, well, let me be a little bit more careful on the training.
Yes.
So in that sense, it was kind of like what you were saying. He knew the smallest ones tend to fail. Let me definitely make sure that the training, the fine tuning rather, has those smaller ones. But if you didn't have that insight, that would be harder. Yes. But then what she was saying is, okay, but you could find that insight. You could look at your current performance and find out where it does feel, where it's weaker. And so you notice the small size, maybe there's other combinations.
I mean, it also is an exercise of aggregation versus a specification, right? If you can get all those CT exams, you create some sort of an amalgam of all of them,
right?
And you create a CT like them in aggregate, right? So if I say, no, I really want to have a Siemens flash look. It's like, what are you talking about? I cannot specify, or I want to have the lesion as opposed to just the CT. We have like 200 pancreatic cases that want to create more of them, right? That maximum we have collected after 15 years, we have 200 great pancreatic cases, but only 200. We cannot train anything with 200. So the question is that how do I, enhance that? And I'm worried about if I give it to a synthetic generation, I'm not sure what would be accentuated in that data as opposed to what I am interested in. So similar to what you have done with long nodules, we need to do with pancreas now.
Yes.
Okay. Any questions? Yeah, no.
So this is going to be a terrible one because it's going to be big.
Okay.
Yeah, I don't know if I should ask, but let's try.
Go ahead and ask. If it's crazy, I'll let you know. Yeah.
We'll let you out.
We are trying to wrap up. Yeah.
Oh, right out.
Yeah.
So if you're given reasonable amount of resource, not the one that you think it's extraordinarily just like NVIDIA, they have all the money, they can get all the resource money can buy. But given a reasonable amount of resource to develop something like something to use in the hospital, like we have enough doctors, enough raw data, and enough computational power. How would you reconcile the percentage of strong, weak, image level, video level, bounding box like type? How do you reconcile that, and how do you reconcile synthesized data? Like, is there a percentage you should use? Because at some point they're going to be chicken egg, right? You use annotated strong labeled data to generate synthesized data, and then use synthesized data to train a model, because this is gonna be a closed loop itself that might not, because the same resource you use twice. You train the synthetic data, and then use synthetic data to train the model, and then back and forth. At some point, it will be garbage in, garbage out. They'll just reinforce each other. So what, like, given all the things you know from all your data, everything, what's the approach that you should take, like, to reconcile all the resources, like strong, weak, synthesized data? How do you, in a project at the beginning, how do you reconcile that?
I think if I have all the resources that you mentioned, the first thing I will do, the 19,000 case labels I got from my rule-based algorithm in the very first study, I will ask doctor to me bounding box for each of the lesions that I find from the radiology report.
It's reasonable, not.
I don't know that. That's an NVIDIA level project. Yeah, you need NVIDIA money.
Yeah. So I think if I know, so because with those data, I worked like for many years with this data, and I know that that 19,000 labels might have covered many of the diseases that we care about. And if I can make strong annotations, even if not the strong, if 50-50 annotations of 10,000 of those cases with bounding boxes, because I know from the radiology report which are the diseases there, I can use many of my resources segmentation detection model. I can find the mostly suspicious one. But if I know that what was the diagnosis for that cases and what was the thinking of doctors writing that part, I might have replicated some of that workflow in default. And a 19,000 strong label will be a huge, I think, driving factor for any model maybe to learn certain pattern that maybe.
So the stronger the better.
Yeah, strong.
The more stronger,
yeah, the more
stronger
stronger is more better. I think so. All the work that we do, we don't have that strong one. That's why we're trying to extrapolate to that positions, right? Strong is always better.
So when you started this project, Dr. Rubin was the radiologist on the study. I want to acknowledge him. He's online. He's paid for a good chunk of your PhD before the CBIT came along. Yeah, I don't know how Dr. Rubin would feel about you asking him to annotate 19,000.
Not too good.
No, he'll say you have reasonable resources.
Oh, okay.
Yeah, like
To make it more reasonable, phrase it more reasonably. So let's say you start with a project focused primarily on weak labeling. So
Yes.
all you have are rule-based, and rule-based is not that weak anymore, right? It's still image level.
Yes.
Sometimes, right? You start with a pre-trained model on something and rule-based or very high level ground truth to train the model, and you're going to add strong label to the data set to train. How do you progress on that?
I think that's the approach I followed from the starting from the DLCS. The limited resources that we have, one med student, one detection model, and a few guidance from the two doctors. We try to annotate that data, and out of that data, all the next models that I have developed has a very high influence that DLCS data that we had. We had very limited amount of very strong data that I can train my model with, and I can also get a reasonable performance that I believe. And then using that model, getting a lot of pseudo labels from different approaches. I actually did that with try-anode and spin,
And then
not MyC.
what's the criteria of deciding to stop adding more strong label? When do you know you have enough?
So like in the current space, the data that we have is not enough. Like, so like 10,000 you have, maybe adding 5,000, maybe not, will not maybe improve. But what if you add 100K more? I think that the log scale that we none of us in the space of CT there yet. I think the largest data out there is just recently released is 50,000, right? But how many patients are there? That is also one question. So that is also one thing. Like, do you need also the patients, not only the CT?
on that clinical curve
Yes.
alone, it was still going up at
Yeah.
100%. You notice, yeah.
All of us.
It wasn't plateau, yeah.
Plateau, yes.
So who knows?
I
Maybe
think
200-300%, 2000%. Who knows? what it
Yes.
would be, yeah. Okay. Well, I think any other important questions? Luke, you look like you're about to jump in.
Not
Okay.
important.
Okay.
I have a quite easy one.
Yeah,
I
go
just
for it.
wanted to
Okay, Brian will have
confirm
last
this-
word.
Among your marvelous, amazing results, one take-home message is that you can take a phantom and create a CT image without modeling a scanner, running through sim or anything like that. And you've shown that such CT images, synthetic ones, are useful for that, is that right?
Yeah, for the synthetic
Yeah.
perspective, yes.
So it makes me wonder then also, why bother with making the phantom? Why not use just the parameter file from Paul's program? It's just,
Yeah.
that's all. I don't expect an answer.
I think, yeah, what you mentioned, that is the best part about this project. I think in the earlier question, I did also mention like very different factors that I lose the control over. I get my benefit over the time, but I lose the quality. I lose the uncertainty of, I get the uncertainty of generations. I cannot say that I'm 100% confident that it will generate that nodule in that place. With the simulations, I think pretty much, you can guarantee me because you made that.
And you answer different questions and work on different solutions.
Yes.
So for certain purposes, yes, if you are hungry for more data for AI training, yes, there is a utility, you demonstrated that. But beyond that, can you tell me what's the difference between photon counting and non-photon counting?
No.
I don't know.
No, yeah.
Or even something very trivial, a different dose, whatever.
I think that
Different modulation.
that is the
Yeah.
kind of synthetic model that's missing.
One day, maybe, right?
Yeah.
Maybe if it's trained on
yeah,
all of that,
yeah.
yeah, you can turn on the.
It might have also missed one thing that apparently I don't have any constraint over the male, female, gender, and other things.
Oh,
We started working on that, but that is not ready yet, so we're not going to.
Or like, for example, what Cindy is trying to do is that if you image the patient 3 times with variability in the patients, how the results will be different.
Yeah.
We cannot answer that question.
all right. Well, thank you all very much. Let's give Tushar one more round of applause.